Hey everybody, happy Friday. Miss you guys, wish I could be there with you. But in my absence, I guess this video is just gonna have to do. Today we are talking about power, which is related to work because it is the amount of work that something can do in a certain amount of time. So far we've been looking at work as a transfer of energy, and that's what it is. But that transfer has been independent of time. It's just been looking at the overall effect moving from one place to another place, something like that. One of our examples that we've been using, and we'll see below, is we had a person picking up a box from the ground versus, you don't have to draw this, but person picking up a box from the ground versus somebody moving a box up a ramp from one side to the other. Okay, so both of these people are doing the same amount of work because they are accomplishing the same task. They're raising the box the same amount, which gives it the same amount of potential energy, but it's probably going to take one of them longer to do that. So power kind of looks at that relationship between work and time. It's a really easy equation. It's power equals the work done divided by the amount of time you do the work in. And its unit is kind of weird. It is the watt, like you see on your light bulb, because that's how much power a light bulb uses, is measured in watts, which is a capital W. And the reason that's confusing is because we also use capital W as the symbol for work, the variable for work. But it's also the unit W for watt. So just make sure you're differentiating between those whenever you're writing stuff down. Okay, so thinking about work, we're going to have to do some comparisons here. We're going to move on down to this part that says consider the following two scenarios. It's going to kind of be the scenario that I previously described. Um, the first one is that you're going to have a person who pushes a 10-kilogram box up a ramp so that it rests at the top, which is a distance of 1 meter above the ground, and this takes the person 20 seconds. Then scenario two is that a person picks a 10-kilogram box up and sets it on a shelf 1 meter above the ground. This takes the person 2 seconds. So things to note here, I'm going to highlight them, are that both of the boxes are 10 kilograms. My highlighter is very large. So we've got 10-kilogram boxes, they're identical, and they're both moving up 1 meter above the ground. Okay, so we've got 10-kilogram box moving up 1 meter above the ground. Scenario one, they're using a ramp. Scenario two, they're just picking it straight up. Now the question is, which person did more work? And I want you guys to pause the video and discuss it to see which one you think. You can pause the video now. All right, hopefully I gave you ample time to pause the video. And hopefully you came up with that they did an equal amount of work. Okay, which person did more work? They were equal. The reason it's equal is because they're accomplishing the same task. Work is a transfer of energy, and since they are both giving the object the same amount of potential energy, they're doing the same amount of work. Now, the next question is which person took more time? Well, it was definitely scenario one that took more time. That's a nice 20 seconds instead of 2 seconds for scenario two. So scenario one took much more time. Now next up, we've got which person generated more power, scenario one, scenario two, or are those equal? I want you guys to pause the video again and discuss that one. Which person, scenario one or scenario two, do you think generated more power? Go ahead and pause that video now and have a nice discussion. All right, hopefully you came up with the person that had more power is the one that was able to accomplish the work faster, and that is in scenario two. All right, so the idea of power isn't that someone is necessarily doing more work, it's that they're doing work faster. It's about the rate that that work is happening or that that energy transfer is happening. So let's take that idea into some calculations down here with the examples. In example number one, it says we have a 40-watt light bulb which uses 1600 joules of energy. The question is, how long is the light bulb on? So we're going to start this the same way as we do all problems with our givens. Our givens that we have here are the 40 watts for the light bulb. You should remember watts means power. So we have power equals 40 watts as a given. And then it says it uses 1600 joules of energy. Um, Now we're kind of bending the definition of work a little bit here. Work is specifically a transfer of mechanical energy, but right now we're just going to kind of bend the rules and say it's any type of energy transfer. And so that 1600 joules is taking electrical energy and turning it into thermal and radiant and that kind of stuff. But we're still going to call it work, even though it does not strictly fall under that definition. Um, so we're going to use work is 1600 joules here. And the question is, how long is the light bulb on? That's a delta T that we're looking for. We're just going to use our equation for today. Power equals work divided by delta T. And we will plug stuff into that. The power is 40. The work is 1600 joules. And we are looking for delta T. Now, I specifically chose this case because it is a little bit difficult on the algebra. A lot of people struggle with finding this delta T. And the most common mistake I see when solving an equation like this is that people think right now over here on the right, we're dividing. So they think you have to multiply to get the thing out of the bottom. And that is true, you do. But most people, or not most people, but a lot of people, the most common mistake with this I see is that instead of multiplying by the delta t to get it out of the bottom, because you can't solve for something that's in the bottom, instead what I see is that they multiply by the 1600, which doesn't cancel anything out because both of those 1600s are on the top. So you got to be really careful with your algebra here. Make sure you're doing it precisely right. We've got 1600 back on top. Sorry, my eraser that I'm using is humongous. I gotta make that smaller real quick. Now it's a little too small. Well, it'll be fine. I'm not gonna cut that out of the video. I'm just gonna leave it in there and y'all can have amusement. Okay, so we're solving the equation 40 equals 1600 divided by delta t. In order to solve that, you have to multiply by delta t on both sides. So I'm going to go ahead and do that. Delta t multiplied by delta t. Don't really have room over there. I'll rewrite it below. We got 40 times your delta t equals, those delta t's cancel out. Now I've got 1600. And your next step to solve for the delta t is going to be to divide by the 40. And if you type that into your calculator real quick or do some quick math, you're going to see that delta t is going to be 40 seconds. And that's kind of the worst case algebraic scenario that you could see there. Otherwise, it's not too hard to solve. But we can take it a step further. Of course, we got to take it a step further. Can't leave it on just super easy. And we're going to look at number 2. This one has us pushing a shopping cart down an aisle in the grocery store at an angle of 25 degrees above the horizontal. It says you push, or you use a force of 60 newtons. If it takes you 25 seconds to make it down a 7-meter aisle, the question is, what is your power output? So we're looking for power. Our only equation involving power is our power equals work times delta T. Now, if you look in at our givens, we've got force is 60. We've got angle of 25 degrees. God forbid an angle. And then we've also got that it's a 7-meter aisle. That's a distance. And we've got the delta T, the 25. So if you look over here at the givens, and remember, you should always write down your givens before you do your question, especially if you're having trouble figuring out where to start. But if you look at these givens, they don't entirely match up with what we've got in our equation here. The delta T is good. We can go ahead and plug that in if we wanted to. But we don't have work, and instead we have all this other stuff, the force, the angle, and the distance. Now, if you remember from 2 class periods ago, we had a definition for work, and that was that work equals F times D times cosine theta. So what I'm going to do with that is I'm going to plug that in over here for the work. Now, if you want to, you can go ahead and calculate this up over here on the side. You can do the force times the distance times the cosine of theta, and that's going to get you a number right here, right now. I'm going to go ahead and plug it into my equation because that's how I like to work. You are welcome to solve for it beforehand. So what that looks like is changing this work into FD cosine theta over delta T. And then I'm going to plug into it like that. So we'll say power equals, the force is 60 times the distance is 7 times the cosine of 25 divided by 25. And those are different 25s as the angle in seconds just happened to turn out as the same number. Now before you type that into a calculator to figure out what exactly the power is going to be, you should check to make sure your calculator is in degree mode. So if your calculator is in radians, it's going to give you some incorrect answer. You want to check right now. Make sure your calculator is in degrees before you do that cosine. The only time you ever have to check is when you're doing trig, but we've got a trig here in this one, that cosine function. So check to make sure you are in degrees rather than radians. And that was mostly me stalling so I can type in on my own calculator at home on my couch. 60 times 7 cosine of 25 divided by 25. And I got to make sure that I'm in degrees, and I am. And I'm getting that the power here equals 15.23 if you round watts. Hopefully that's what you guys are getting as well. Okay, so we're going to move on to the back. Hopefully y'all are doing okay. If you're having questions, you can email me once we're done with the video. All right, on the back, starting with number 3, we've got a 15-kilogram dog that starts at rest and speeds up for 10 seconds. Question is, if the power output of the dog is 27 watts, what is the final velocity of the dog? And we think, oh no, oh my gosh, we got a lot going on. Let's write down the givens, but these sound different than the previous ones. Starting with mass, we have 15-kilogram dog. Speeds up for 10 seconds, that's delta T. It says the power output of the dog is 27 watts, so power is 27. And the question is, what is the final velocity of the dog? So we're looking for that VF. And we did have one other hidden given in there, that it starts at rest. So that means your VI is 0. And we have a lot going on in there. We've got a VI, we've got a VF, we've got a power. So there's no equation that involves all of those things. That means we're going to have to mix and match on our equations. So when you're picking an equation to go with this, obviously we're going to have to use the power equation. Power equals work over time. Since we've got power, that's the only equation that involves the power. But if you look at that equation, the power equals work over time, the only variables that we have out of it are the power and the time. That means we're probably going to have to look for the work and somehow relate the work to these other variables. Now, you should also think about what types of energy are going on here. Well, with our dog starting at rest and speeding up, it doesn't mention anything about going up a hill, going up a ramp, any kind of height change. So this is really only dealing with kinetic energy, not potential. There's no springs involved either. So it's not spring potential or gravitational potential. We've just got kinetic energy going on. So you're going to want to use this power equation in conjunction with something kinetic. And that kinetic energy, it is changing since it starts at rest and it speeds up. So you need to find the relationship between the kinetic energy and or the kinetic energy initial and the final using the work, and that is the work energy theorem for the kinetic energy. That K, or sorry, not K, that 1/2 mv I squared plus W equals 1/2 mvf squared. We did that quite a while ago. Now you could technically use your big energy conservation one, except the both potentials there would cancel out and would just turn back into this equation again. So that's up to you how you want to look at it. It'll boil down to this in the end. So we are going to need to solve for this final velocity. But before we can solve for the final velocity here, we got to have the work. We got to get the work from over here in the power equation. That's the one we're going to do first. So we've got power is 27, and that equals your work divided by the time. Time is 10, it says. We're going to do a nice multiplication there for the algebra. And hopefully you can do that one in your head. 10 times 27. Your work is 270 watts. Sorry, not watts. Joules. I'm not doing good on units lately. There's my tiny eraser again. 270 joules. So that's work. But we want to know the final velocity, so we've got to take that work and plug it in up here with the stuff that we know from the beginning. Plugging into this equation, this is the work energy theorem for kinetic energy. It's 1/2 times our mass of 15 times our initial velocity of 0. So dog was at rest. It had no kinetic energy. That's just going to cancel out. Plus, we did 270 joules of work, or the dog did 270 joules of work. And that equals 1/2. Our mass is still 15 times the velocity final squared. Velocity final is what we're looking for, so we leave it as the variable. Over here on the left, this part, the kinetic part, is going to cancel out because it started at rest. It had no kinetic energy. And then it did 270 joules of work in order to get to this final velocity. So now it's got 270 joules of energy from the work. That equals 1/2 times the 15, which is 7.5, times the VF squared. In order to solve that for the VF, you have to divide by the 7.5, so those are going to cancel. That's going to give you VF squared, so you're going to have to square root. Now, for time's sake, I am not doing the intermediate calculation of the 270 divided by 7.5 and typing it in. Oh, it turns out to be 36. How nice. So we're doing the square root of 36, which is 6 for your final velocity there. It should be meters per second. Once again, not doing good on units today. Got 6 meters per second for the velocity on this one. But you had to use your power equation in conjunction with your work energy theorem for the kinetic energy. It's kind of a two-step thing. You got to do a lot of thinking there to figure out your course of action. Now we're going to go ahead and move on. I know that was probably a bit more than you anticipated on a day that I was out, but we've actually got just a little bit left to do. And that's with a derivation. We haven't done too many derivations in this class. That's basically where we're going to start with an equation and turn it into some other equation. And we're going to do that with power. So power, we said, is work over time. Not too bad. But earlier we saw work broken down into something else, and we're going to break it down into that now. Work can be force times distance times our cosine of theta. And if we're still setting that equal to power, it's still got to be over the delta t, so that everything's nice and equivalent. And we've already done that once, but there's one little term in here that we can change around. I remember from way back in the day, we had a term for distance over time. We haven't seen it in equation form in a long time, but we use it pretty frequently. The distance over the time is the velocity. That's what distance over time is. So we've got here, we could replace that distance over time with a velocity, and leave our force and our cosine theta there, and that gives us power in a new set of givens. So power could either be work divided by your change in time, or it could also be equal to F times V, that's force times velocity times cosine theta. Now note, this can actually only be evaluated if it is moving at a constant velocity. It's possible for this to work out when it's not a constant velocity, but if you do that, it involves calculus, which is not within our scope. So you could only really use this on a constant velocity when you have just one velocity to plug in there for the v. So we're going to look at how that would work with example number 4 here. I'll leave that equation up there. Example number 4 says a kayaker paddles with a power output of 50 watts to maintain a steady speed of 1.5 meters per second. Question is, find the force exerted by the kayaker. Assume the force is acting parallel to the motion. So here our givens are that the power is 50 watts, and we've got a steady speed, so we're allowed to use this because that's a constant velocity. Got a steady speed of 1.5 meters per second. So V is 1.5. The question is, what is the force? And it also says, sorry, assume the force is acting parallel to the motion. And parallel to the motion is going to mean that our theta is 0. So that's like the force is going this way, the distance is going that way. Those are parallel, 0 degrees apart. And now all we've got to do is plug those into our handy dandy equation that we just derived. That's P equals FV cosine of theta. Our power was 50 watts. Our force is unknown. Our velocity is 1.5. And our cosine is of 0. And when you take that cosine of 0, that's really just going to be 1. So this is force times 1.5 times 1. The 1 really has no effect. Got 50 equals 1.5 times the force is essentially what it is there. Now we're going to divide by that 1.5 on both sides to get the force. When you type that into a calculator, should turn out as 33.3 repeating, which I'm just going to round off here to 33.3 newtons. And that's the whole deal. All right, now on your practice, you've got power questions on the front. They may challenge you a little bit because they mix and match some of our old equations, might draw some of those in. And then on the back, you've got 3 questions about the conservation of energy, which was what we did last class. Now I am planning on taking these for a grade, or I'm going to take these for a grade. So you're going to need to turn them in by the end of class. Our sub, Mr. Reynolds, is going to pick them up by the end of class, so make sure that you are working diligently on them. The answers to all of them are in Google Classroom, so you can check yourself. Now, it is currently 11:09 p.m., and I have just recently typed those answers in, so it's possible that I missed one or maybe two. I don't know. So if you really feel that you have a question correct and that I have it wrong, please email me and I will check it. But what I will be grading when I grade these practices is your work that you show. So if you do not show any work, I cannot grade your work. And since you already have the answers, I'm not grading your answers, I'm grading your work. So you need to make sure that you show that, and that includes the graphs that are on the back. You got to do the bar charts. You're going to have to do them for points on the test, so you're going to have to practice them at some point. Please do them today on your practice. I know I'm not there, so you can't ask as many questions, but please email me if you've got them, and I'll do my best to respond to that. Otherwise, turn them in, and if we need to do any kind of work on those, we can work on them on whatever day. I'll see you next on Tuesday. We'll take a look at them on Tuesday. So you guys, please put in your full effort, and then after that, have a great weekend. I'll see you next week.